So last time we were discussing the Compton effect, which is the dual nature of the photon. So we have seen up to here that the electron, the photon has a dual nature. It can act as a wave as well as particle. So in the wave nature of photon, we have seen there are two applications in which the photon act as a wave. One of the application is the interference and the other application is diffraction phenomena. So these are the two applications in which the photon act as a wave. So now there are two other applications in which the photon act as a particle, which we have seen that in the photoelectric effect and in the Compton effect, the photon act as a wave, as a particle, sorry. So now the question is that if the photon, which has a dual nature, then according to the DeBroglie hypothesis, okay, why not the particle has a dual nature? It means if we say that the electron, according to the DeBroglie hypothesis, it means if the photon has a dual nature, then why not the electron, which is a particle, has a wave nature? So now if we say that this is the particle like electron, for example, if the electron is moving with a certain velocity v, then it may be possible that it can associate a wave. So according to the hypothesis which was given by the DeBroglie, if the electron, which is a particle, if it is in a motion and associated a wave, then its wavelength will be equal to the lambda is equal to h upon p. This lambda is the wavelength of the particle, which we call it as a, let's say, one of the particle is electron. So h is the Planck's constant and p is the momentum of the electron. So this lambda, this can be written as h upon n into v. M is the mass of electron and v is its velocity. So this indicates that the wavelength is inversely proportional to the velocity. So now here, the wavelength is inversely proportional to the mass. It means if we have a different particles like electron, proton, neutron and etc. So the proton has a higher mass than the electron. So it means if both are moving with the same velocity, if electron and proton both are moving with the same velocity, then the wavelength of proton, whose mass is higher, so the wavelength must be smaller than the wavelength of the electron. It means if the mass is higher, the wavelength is the smaller. So the wavelength of the particle is inversely proportional to the mass. So this was just a hypothesis. DeBroglie proposed that if we say that the particle has a dual nature, it can act as a wave as well as a particle, then if it acts as a wave, then its wavelength should be equal to this. So this wavelength is proved by the experiment which we call it as a Davison and Germer. So Davison and Germer explained that Davison and Germer performed the experiment that when the electron is fired from, this is, let's say, the electron is coming from the filament here, this is the cathode. Cathode is the emitter of electron. When this cathode is heated by a certain potential, which we call it as a, let's say, this is the filament. When this filament is heated, as a resultant, it heats up the cathode, and this cathode emits out the electrons. These electrons are emitted out from the cathode. So now here we have a crystal, and we call it as a, this is the nickel crystal. When electron falls on the surface of the nickel crystal, as a resultant, it is scattered at a certain angle. This is the angle of scattering, let's say theta. And we have seen that this scattered electron from the nickel crystal gives the pattern, and which pattern is in the form of the rings, circular rings, bright and dark rings, or it may be bright and dark bands. So these bands and rings both are due to the interference pattern of the electrons. And we know that the interference is the phenomena which exists in the form of the form of the wave nature. It means if the particle has a wave nature, then this behavior is possible. The interfering behavior is possible. So this interference behavior gives rise the verification that each particle, each electron is associated a wave, and this interference pattern gives the proof of the wave nature of the particle. So now there are certain quantitative analysis. So now when the electron is scattered from this, it gives rise the interference pattern. So according to the interference pattern, there is a condition for the interference, for the constructive interference, that d sine theta is equal to m lambda. D is the spacing between the planes. Here we have a different crystal planes, and d is the spacing between the planes, and sine of angle theta is the angle of scattering of the electron from the surface, and m is the order of the fringes. If we say that it is the first order, so m is equal to 1, and lambda is the wavelength of the light. So here d, which is the spacing between the planes, this can be written as d, which is equal to, for the, let's say, for crystal, here for NaCl crystal, this B is equal to 0.215 nanometer. This is the spacing between the solids. So the angle of scattering theta is equal to approximately 52 degrees, because this scattered electrons was collected at an angle of 52 degrees in this experiment. So as a resultant, this formula gives the lambda wavelength of d is equal to, let's say, d is equal to here, sorry, theta is equal to here from this formula m lambda upon d. So this can be written as sine inverse. So here m is equal to 1. So this theta is equal to sine inverse lambda upon d. So this theta from this relation is approximately equal to 51 degrees. So from this relation, from the experimentation, it is proved that the theta angle of scattering is 51 degree, and the experimental verification in which theta is equal to 52 degrees. So this is the theoretical calculation, and this is the experimental observed value. So it means both results are almost similar within the experimental error. So then we can conclude this from this experiment performed by the Davison and Germer, that each particle is associated a wave, and its wavelength is associated through this formula. How to calculate wavelength by using this formula? Here, if we say that H is the Planck's constant, m is the mass of electron, and v is the velocity of the electron. Here, the electrons which are coming out from the cathode is accelerated by a certain potential or voltage, which we call it as a V. When electrons are accelerated by a voltage, it will gain a kinetic energy. So you know that the voltage potential into charge is equal to kinetic energy, which is equal to 1 upon 2 mv square. From this equation, v, which is the velocity, which is equal to 2 potential into charge upon m into square root. From this relation, we can calculate the velocity. If we plug in the value of velocity over there, we can get the wavelength. So lambda is equal to the h upon m into v. V is equal to 1 upon 2 potential into charge into m square root. So here, from this relation, you can calculate the wavelength, and the wavelength is similar as that obtained from this relation, from the relation of the diffraction. So this indicates that the DeBroglie hypothesis that each particle is associated a wave and its wavelength is equal to h upon mv is proved through Davison and Germer experiment. So now we believe that every particle is associated with the wave. Now question is that when the particle act as a wave, when the particle act as a particle, the action or the phenomena, it depends totally the phenomena. If the phenomena gives the interference pattern or diffraction pattern, this indicates that in this experiment, the particle act as a wave. But if the phenomena in which it act as a collision, when one particle collide with the other particle, so it act as a particle. So it means this depends upon the experimental evidence whether the particle act as a wave or act as a particle. So now we say that each particle is associated with the wave. Now question is that if the particle is associated with the wave, then its wavelength is equal to this. So now what about the motion of the particle? It means there are certain equations which represents the motion of the particles. Here if we look here, so now here, if we say that this is the particle and it is associated with the wave, then what is the function of this particle? Where is this particle within this wave? This is the question mark. It means if we say that this is the wave associated with this particle electron. So now in this whole train of the wave, where is this particle? We cannot measure the exact location of the particle because you have an equation of motion which is equal to, you know that x is equal to vt, vf is equal to vi plus at, s is equal to vit plus half at square, vf square minus vi square is equal to 2as. These are the certain equation of motion which describe the motion of the object. So now the question is that whether these equations are applicable for the particle if the particle act as a wave or not. So the answer is this. Here s is the distance, s is showing the location. So these equations, which are the equation of motion for the visible object, for the macroscopic object, But for the microscopic object, which cannot be seen by the naked eye, so this equation is no more valid. So now we have an equation and we call it as an equation of state, or we call it as a wave function. So now what is the wave function or state function? So now here we are discussing the wave function. Here the wave function, it is actually, it is the state function which indicates, which shows the state of the particle. फॉर एग्जाम्पल आप पढ़ के आए हो कि ये आपके पास कोई भी वेव है, दिस वेव is moving along x-axis. Let's say the wave is moving along x-axis and it is a function of time because it varies with the time. So this is the y-axis, let's say. So this is the maximum amplitude. The maximum displacement from the equilibrium position is known as its amplitude. So we know that y, which is a function of the position and time, which is a function of x and t, is equal to a. A is its amplitude, which is the maximum displacement from the equilibrium position, which we call it as a or a naught, into sine of angle kx minus omega t. This is the simple equation of the wave or waves in the string. किसी भी स्ट्रिंग में वेव है तो उसका जो फंक्शन होता है वो इसके बराबर होता है. तो सिंपली k is the wave number, k is the wave number, and this k, which is equal to 2 pi by lambda, and this omega is equal to angular frequency, which is equal to 2 pi f. F is the frequency, omega is the angular frequency. So this omega is known as angular frequency. Omega is the angular frequency. So here k is the wave number. So this portion represents the motion of the wave along x-axis, and this portion represents the time dependent function of the wave. So this is the space dependent function and this is the time dependent function. But in this case, the wave function, which is the function of state and time, position and time, this can be rewrite as with the function of psi. In the case of particles, this is like a waves in the string. If the particle is moving, then the state function is representing by the function psi. This psi is the function of position and time, which is equal to e raised to power minus iota kx minus omega t. This k is again the wave number, which is equal to 2 pi by lambda, and this omega is again the angular frequency. So now here, this psi, which is a function of position and time, in 3 dimension, this is 1 dimension. It is the 1 dimension. It means the wave is moving along x-axis. It means the wave is moving along x-axis, which is a function of x-axis, and this is a function of time because it is moving with the time. Now, if the wave is in the 3-dimensional motion, if the wave has a 3-dimensional motion, then the psi can be written as a function of x, y, z into time t. This can be written as e raised to power iota kx, ky, kz minus omega t. So this is the along x-axis, y-axis, and z. In general, this psi in three-dimensional is written as r into t. R is the position vector which gives the three components x, y, and z. This can be rewritten as psi naught. Here we have a function psi naught e raised to power iota k into r minus omega into t. So here, this is the three-dimensional. So now in case of here, in case of one dimension, we have two parts. One is the position dependent part, psi x into t. This can be written as psi naught e raised to power iota kx into e raised to power minus I plus iota omega t. So this is divided into two parts, e raised to power minus iota kx, e raised to power minus into minus plus iota omega t. So this is the space dependent part of the wave function. This is the space dependent part of wave function, and this is the time dependent part. So here we have a two parts. One is the space dependent and other is the time. So if we say this psi, which is a function of x only, because it is not a function of time, if we say that this is not a function of time, it is a function of position. इसको space dependent भी कह सकते हैं, position dependent भी कह सकते हैं. We may say it's a position dependent. So this psi of x can be rewritten as psi naught e raised to power minus iota kx. So this is the simplified form of the state function and wave function. So this is the state function for a free particle. This is the one-dimensional wave function for free particle. So this is the one-dimensional wave function for the free particle. So now here we say that this is the wave of a particle associated with the particle. This is the, let's say, any wave which is associated by a particle. So now in this whole wave, where is this particle? Particle कहाँ पे है यहाँ? How to find out the position of the particle? We generally say that where the amplitude is maximum, here the amplitude is maximum, the most probability of the particle is to be there, where the amplitude is maximum. It means the position of the particle cannot be defined with a certain value. So there is always a probability of finding the position of the particle. So the position cannot be measurable with the exact value. So it means here we will define the probability of finding the position of the particle. So here in this case, so when the particle acts as a wave, then the position of the particle can be determined with a certain probability. Then the position of the particle can be determined with certain probability. With a certain probability. And what is that certain probability? Psi P is the probability which is the product of psi wave function, which is a function of position and time, into conjugate of psi, which is a function of x and t. This is the probability of finding the particle within the position x and x plus dx. So this is the way to find out the probability. So P is equal to, what is the psi for free particles? Psi naught e raised to power iota kx minus omega t into what is psi conjugate psi star, which is equal to psi naught star e raised to power, here this is the iota kx e raised to power minus iota kx plus omega, minus omega t. So this minus minus, when you multiply, it becomes 1 psi naught into psi naught star, because this and multiplying with this gives you the 1. So as a resultant, the P is equal to this into dx. So P, which is equal to psi naught square, because psi naught into psi naught star is equal to psi naught square. So here the probability of finding the particle within the displacement dx is equal to this. This is the probability of finding the particle within the displacement x. So now here, this is the probability. If we divide probability with the dx, this gives you a probability density. So the probability is equal to psi naught square. This is the probability density, which is equal to psi naught square. So now when we say that the electron acts as a wave, then there is a certain uncertainty principles, which we call it as a Heisenberg uncertainty principle. Heisenberg uncertainty principle says that we cannot measure the exact position and momentum of a particle simultaneously with 100% accuracy or with 100% precision. So here, so when the particle acts as a wave, जब वो wave है, act as a wave, then position and momentum cannot be measurable with precision simultaneously. So here, this delta t into delta x is approximately equal to or greater than h bar. So the momentum and position cannot be measurable simultaneously. If we measure the momentum, there will be uncertainty in position. If we measure the position, there will be uncertainty in momentum. This is the momentum along x-axis. So the momentum of along y-axis, the position along y-axis cannot be measurable simultaneously. The momentum along z-axis and the position along z-axis cannot be measurable. So here, the momentum along x-axis and position along y-axis is measurable. But the both parameter along the same axis is not measurable. Similarly, this is the position and momentum uncertainty principle. So we call it as a Heisenberg uncertainty principle. This is known as a Heisenberg uncertainty principle. So there is another principle which we call it as the energy time uncertainty. Energy time uncertainty principle, which is equal to delta E into delta T is approximately equal or greater than H bar. ये H bar is equal to आपको पता है H upon 2 pi. So here it means the energy of an electron at an excited state and the time of stay of electron in any state cannot be measurable simultaneously. If we measure the energy, there will be uncertainty in time, stay of time or lifetime of the electron in any excited state. If we measure the time, there will be uncertainty in the energy, and we call it as a degeneracy in the energy state. So these both quantities is not measurable simultaneously.